Hello all, welcome to Advanced Engineering Physics lecture series Quantum Computing 2. This is Dr. S. Deepthi, Assistant Professor in Physics, Department of H&S, MLR Institute of Technology. So, in the previous lecture, we have learned about quantum, introduction of quantum computing. Now, in this video lecture, we are going to learn about linear algebra in quantum computing, how linear algebra is used in quantum computing. What is linear algebra that you are learning from your childhood onwards, right? So, linear algebra provides the mathematical foundation of quantum computation. Quantum systems are described using complex vector spaces. Physical operations are represented by matrices. Okay, this is the matrix representation. Quantum computing involves in first one is a quantum state, vectors in Hilbert space. Next one is quantum operations, unitary matrices. Third one is multiple qubits, tensor products, and the fourth one is projection operators. These are the four systems that we are going to use. Okay, now in this what is here? So linear algebra concept, a vector space, a vector in a vector space. So what is a vector? Vector means it has its physical meaning also. What is a vector? We have studied in physics and in also mathematics also, right? So a vector means which has both directions and also it is a directional direction. It has both direction and magnitude. It is a vector in according to the physics. So here also we are using the physical meaning of a vector. So linear algebra concept, a vector in vector space. A state space can be described by Hilbert space, which is a complex vector space with a inner product. Okay, Hilbert space is a complex vector space with a inner product. We'll go across. So quantum computing analog, the qubit, quantum bit. Okay, a classical bit is either 0, 1 or 1. The qubit is a vector in a two-dimensional complex vector space. So what is a qubit? It is a two-dimensional complex vector space. The Dirac notation or bracket notation. Now, so going in the concepts of linear algebra, what we are going to learn? So we are going to learn about a Hilbert space. We are going to learn about a system where the vector notation works, how the vector notation works, and also how this notation keeps us mathematically into the quantum computation. Okay, so first let us learn about Dirac notation. So Dirac notation or bracket notation, okay, it's a powerful, concise mathematical language used extensively in quantum mechanics and quantum computing, designed to simplify calculations in complex vector spaces, Hilbert spaces. It is invented by physicist Paul Dirac. Okay, so this is Dirac equation is in a quantum mechanics and this is being used in quantum computation. Okay, the ket state vector, ket is represented with, okay, one straight line, psi followed by greater than symbol. This is the ket representation. Okay, so this represents a quantum vector space in Hilbert space. This is the abstract representation of a system state. Okay, linear equivalent, a column vector. So normal equivalent will be a column vector. So ket 0 and ket 1 are the we are only having two states. One is 0 and 1. So here in quantum computation we use only zeros and ones, which where they are called as ket 0 and ket 1 or bra 0 and bra 1. Okay, so here we are going to use ket 1, that is equals to, that is represented as 0, 1, and ket 0, that is represented as 1, 0. Is it okay? Next, so a general superposition of state, psi is equals to, ket psi is equals to alpha ket 0 plus beta ket 1, that is alpha and beta. Okay, so bra, the dual vector. So bra means what? Represents the dual vector or a linear function corresponding to the ket. It is a complex conjugate transpose of a ket. Okay, linear algebra equation equivalent, a row vector that is Hermitian conjugate or conjugate transpose of a column vector. So it is represented with psi is equals to, which is the transpose of ket. So single qubit is brass I is equals to alpha star plus beta star. Okay. Now, linear algebra concept. A linear transformation or operator represented by a matrix. Okay. This is matrix means zeros and ones, column matrix and row matrix. Both we can have in this representation. Quantum computing analog. Quantum gates, unlike logical gates in classical computing. They are unlike classical gates in classical computing. Quantum operators must be reversible, no loss of information, which means the matrices represented must be unitary. Unitary matrix is U transpose and its universal is equals to U dagger. U dagger into U is equals to I. I is the our 1001 unitary matrix. Okay. Now, linear algebra concept, tensor product, used to combine the smaller vector spaces into larger one, combine the smaller vector spaces with larger ones. Quantum computing analog, multi-qubit systems and entanglement. The state space in qubits is a tensor product of n single qubit spaces. The dimension of space grows exponentially 2 to the power of n. So, the state 0, 0 means qubit 1 is ket 0 and qubit 2 is ket 0. Okay. Qubit 1 is ket 0 and qubit 2 is ket 0. So, ket 0, 0, this is the tensor product of 0, ket, tensor product is represented like this cross with circle. Okay. So, ket 0, 1, 0, 1, 0. 1 into 1, 0. 0 into 1, 0. 1 into 1, 1. 1 into 0, 0. 0 into 1, 0. 0 into 0, 0. This is the final answer. Okay. It is easy matrix multiplication itself. Understood about tensor product? Tensor product just multiplies each and everything that we are going to see here. If we take one set of ket 0 is tensor producted with another ket 0, then what happens? 1 into 1, 0, 0 into 1, 0. Then it will come as a single column matrix 1, 4 zeros. Okay. So, linear algebra concept here also. Projection operators. Next to come is projection operators or projectors. A matrix P such that P square is equals to P. The square is itself is equals to the same thing. So, quantum computation analog. When you measure a qubit, ket psi is equals to alpha 0 plus beta ket 1. The quantum state collapses to 0 or 1. The probability of getting the result is given by square of magnitude of amplitude, alpha square. Okay. Now, so this is a simple representation where we can represent. In the next video lectures, from the next video lecture onwards, we are going to have the tensor products, we are going to have the linear algebra combinations, and we are going to have the superposition of states and so on. So, this is the simple matrix representation. Here we have learnt in this video lecture. So, linear algebra and quantum computing. Next video lecture, you are going to learn about Bloch's theorem and quantum concept of quantum computer. So, this is Bloch's theorem is different. Bloch's sphere is different. Bloch's sphere is represented with the qubits in 0 and 1, the probability of the states of qubits and so on. Okay. Thank you.